Welcome to the office. We want to take a look at an extension or a refinement of our topic of orbits. So in our orbits, so for our last example, we said, all right, here's a set of elements that the permutation sigma just moves these elements around from one to another. Excellent. And the way that we found them was we said, all right, well, this one goes to that one, and then this one goes to that one, and this one goes to that one, and so on. And the way that we wrote it down kind of gave an ordering of how sigma moved along those elements. The problem is that set notation doesn't require a particular ordering. For example, if we consider our previous example, then we might be able to notice. So here, let's look at this permutation, and let's look at this set here. We know that the set containing 3, 10, and 7 can certainly be written as, I don't know, 10, 3, 7. These two sets are exactly the same thing because set notation doesn't care about ordering. However, sigma does not take 10 to 3. It takes 10 to 7. It does not take 3 to 7. It takes 3 to 10. And it does not take 7 to 10. It takes 7 to 3. So this was obtained by considering what sigma does to the elements. So we want to take this refinement and say, well, I care about this ordering. How can I express something where I care about the ordering? Well, I can do that by using parentheses, right? An ordered n-tuple rather than just a set. So I'm going to change my notation to make that distinction that I care about the ordering. All right. So what is a cycle? Let's look at the formal definition. We'll introduce that notation with parentheses, and then we'll kind of work backwards to go from parentheses to this representation. All right. A permutation is a cycle if it has at most one orbit containing more than one element. So we have a bunch of orbits. All of them have just one element, except one particular orbit, and that contains more than one. When we have that, then it is called a cycle. And the length of the cycle is the number of elements in its largest orbit, right? That orbit that contains more than one element. All right. So we want to observe that this example of a permutation is indeed a cycle. We will write it in cyclic notation, and we will write the length of that particular cycle. In order for us to observe that sigma is a cycle, we have to identify the orbits of the cycle. Or sorry, orbits of the permutation. So what are the orbits? Well, 1 gets sent to 1. I'm marking these off as I write them down here. 2 gets sent to 5. So 2 goes to 5. That takes care of 2 and 5. 5 gets sent to 3. 3 goes to 8. 8 goes to 9. 9 goes to 2, and that's back where we started. So in order for this to be a cycle, I need all of the remaining orbits to contain just one element. And indeed, 4 goes to 4. So that is a single orbit. 6 goes to 6. My apologies here. I made a typo. I had 6 and 6. So 7 goes to 7. Otherwise, that wouldn't make sense for us. So 7 goes to 7. That's taken care of. And then 10 goes to 10. So those are just one element orbits. The only orbit that is not just one element is this one. So I want to write sigma in a way that I actually care about ordering. Again, I can write this particular set in many different ways. I found it by saying 2 is related to 5, 5 is related to 3, 3 is related to 8, and so on. Right? Sigma takes 2 to 5, sigma takes 5 to 3, sigma takes 3 to 8, sigma takes 8 to 9. And that specifically is what I want to represent. I want to say sigma takes 2 to 5. Sigma takes 5 to 3. Sigma takes 3 to 8. Sigma takes 8 to 9. And sigma takes 9 back to 2, so I end the parentheses. And this is cyclic notation. Excellent. this cycle, sigma, has a cycle length of, well, how many elements are in there? 1, 2, 3, 4, 5. There's a cycle length of 5. Fantastic. Notice that if you take sigma to the 5th power, 2 would take sigma would take 2 to 5, it's 1 iteration. 5 to 3, it's 2 iterations. 3 to 8, that's 3 iterations. 8 to 9, that's 4 iterations, and 9 back to 2, that's 5 iterations. So saying that it has a length of 5 is also referring to the order of the element, right, this element of the permutation group. So that's kind of cool, a little bit interesting, that we'll talk more about later. All right. And just to help us reinforce this notation, let's say that I am looking at sigma, which I can write as, 1, 4, 2, 3 in S8. So this is where it's important that I specify that I'm working in the symmetric group with where A is 8, right? It's the elements 1 through 8, numbers 1 through 8 rather, because there are many missing things here. I don't see anything above 4. So what we end up with, if I wanted to write it in our old notation, so this will be our new notation, cyclic notation. This will be our old notation for a permutation. I want to know where 1, 2, 3, 4, 5, 6, 7, and 8 all go. Well, 1 goes to 4, 4 goes to 2, 2 goes to 3, and 3 goes to 1. And that's it for our cycle. We still have the elements 5, 6, 7, and 8, but since they're not listed in the cycle, we know that they are all fixed. 5 goes to 5, 6 goes to 6, 7 goes to 7, and 8 goes to 8. And that's all that we're looking for. Excellent. That's all that I wanted to share for this video. So we'll talk a little bit more in our next video about cycles, trying to work on developing that cyclic notation. So I'll see you back here in just a moment.